must be thoroughly checked before the job can be executed. Even very minor data errors like a typo in the dates can actually cause the batch job to not run. Now, in stream processing, each new piece of data is processed as it arrives. So for example, as we ingest that data, we process it in real time. And so streaming handles data in real time. Unlike batch processing, there's no waiting until the next batch interval to then process that data, because we're actually processing each individual pieces of data item as they come in. And so stream data processing is very, very useful for scenarios where we're dealing with new dynamic data that is being generated on a continuous basis. Lesson 2, exploring roles and responsibilities in the world of data. So there are 3 key roles that deal with data in most organizations, and these are data administrator, data engineer, and data analyst. As a data administrator, their main role is really to manage databases, assign permissions to users, store backup copies of data, and restore data in the case of any failures. As a data engineer, their role in data is to work with the data, to apply data cleaning routines and transformations, build out those data pipelines and processes, identify business rules, and really turn data into useful information and prepare it for data analytics workloads. And as a data analyst, their role is really to explore and analyze the data by creating visualizations and charts which help enable an organization to make better and more informed decisions. So some of the common tools that a database administrator might use includes Azure Data Studio, SQL Server Management Studio, as well as the Azure Portal or the Azure CLI. So a database administrator will need to use these tools to configure the overall availability of their data servers and databases. They're responsible for maintaining consistent performance and optimizing the data servers and databases. So they need to work with the stakeholders to ensure that policies are implemented, that the tools and processes are set up in place, and that backup plans are available to recover any data servers or databases that might fail due to some error because of some natural disaster or human-made error. And so they're also responsible for the security component of the data servers and databases, which means they're the ones who grant access rights to users to determine who gets the right to access databases and who doesn't. Some of the tools that a data engineer might use includes Azure Synapse Studio, SQL Server Management Studio, as well as the Azure Portal and Azure CLI. So as a data engineer, their responsibility includes maintaining and managing data privacy within the cloud, as well as on premises. So they're also responsible for managing and monitoring data stores, the data pipelines, making sure that the data performs as expected by doing a combination of cleaning and transformation on the data to prepare the data for data analytics queries. Some of the common tools that a data analyst might use includes Power BI Desktop, Power BI Servers, and the Power BI Report Builder. So data analysts are typically those who design and maintain scalable business models with data. They might also engage with cleaning and transformational activities to further advance their analytics or build reports and visuals to help business decision makers digest that information and the results in a more visually pleasing way. The main goal of a data analyst is really to turn the raw data into insights based on the business's requirements. And then that insight can then be turned into actionable decisions. Lesson 3. Describe concepts of relational data. We'll start with tables. So a table is where data is stored in relational databases. They consist of rows and columns, and all the rows have the same number of columns. Each of the column is defined by a data type. Now, one of the main benefits of a computer database is that they make it easy to store information so that it's quick and easy to find. For example, an e-commerce system might use a database to record information about the products that this particular e-commerce site or organization might sell, as well as some of the details of their customers and the orders that they've placed. And so we have a customers table here, which stores the customer ID, the customer name, and the customer phone number. Now, a relational database provides a model for storing this data and query capabilities that enables us to retrieve this data very, very quickly. So let's say I wanted to look up customer ID 106 from this table. I can see that it's Alex Peterson. In a relational database, you typically model collections of entities from the real world as tables. So for example, a customer is an entity, therefore we create a customer table. An entity generally describes a thing about information which we want to hold inside a database. In the e-commerce example here, we might also create tables for products and orders because they are also entities in the real world. Now, table contains rows, and each of these rows represents a single instance of an entity. So what that means is each row in this customer table contains data for a single customer, and each row in the products table will define a single product in the products table, and each row in the orders table will represent an order made by that customer. Now, the rows in a table can have more than one columns that define the properties of the entity. So the properties in this case would be customer ID, customer name, and customer phone number. And all the rows in the same table will have the same number of columns. And some of these columns are actually used to maintain relationships between tables, which is where relational databases or relational model gets its name from. Typically, when we're designing a relational data model, we need to normalize the data so that we can reduce storage, we can avoid data duplication, and improve data quality. So, for example, instead of storing a replica of the customer's details in the order table, we would split out that data into two separate tables and reference the customer table from the orders table. So the orders table now contains both a customer ID and it also contains a product ID. Now the customer ID relates to the customer ID in the customer table. And similarly, the product ID will relate to the product ID in the products table. And so we typically design a relational database by creating these relational data model. And each table will have these primary keys. So the customer ID in the customer table, order ID in the order table, product ID in the product table. These are all examples of primary key. And the primary key is then used to associate with a foreign key in another table. And so the customer ID and the product ID in the orders table are foreign keys. And this foreign key references the primary key and is used to establish that relationship between tables. Now, another concept to know in relational data is indexes. So an index helps you search for data in the table. You can think of an index over a table like an index at the end of a book. So the index at the end of a book helps you find certain pages relating to certain topics or subjects, so that when you want to find a reference to a particular topic or a subject, you simply have to look it up in the index at the end of the book and then go to that specified page number. Imagine that you didn't have this index. So to find out about a particular topic or subject, you'd have to read through the entire book to be able to find that information out. And so similarly, when we create an index in the database, we specify a column from the table where this index contains a copy of this data in a sorted order with pointers to the corresponding rows in the table. And so when a user runs a query that specifies this column in, say, for example, the where statement clause, the database management system can then use this index to fetch the data much more quickly instead of having to scan through all the tables in the entire database row by row to find out that information. So you can create many indexes on a table. Say, for example, if we wanted to find all the customers for a specific region, then we can create another index on the customer ID column from the customers table. But indexes are not quite free. So an index would consume additional storage space, and each time you do an insert, update, or delete to a table, the indexes for that table needs to be maintained. And so this additional work can actually slow down your database operations. And therefore, if you're deciding to use indexes, you must strike that balance between having indexes to speed up your queries versus the cost of performing your database operations. Now, typically in a table that is read-only or contains data that is modified infrequently, more indexes will actually help improve the query performance. If a table is queried infrequently, but it's subject to a large number of inserts, updates, and deletes, then creating indexes on that table can actually slow your database systems down. Now, a view is a virtual table based on the result set of a query. So in the simplest case, you can think of a view as a window on specified rows in an underlying table. So you can query the view and you can filter the data in much of the same way as you would with a table. Now, a view can also join tables together. So if you regularly need to, say, for example, find the details of customers and the products that they've ordered, you could create a view to do so. Lesson 4, exploring concepts of non-relational data. Now, in a non-relational system, you typically store the information for entities in collections or containers rather than relational tables. So two entities in the same collection can have a different set of fields rather than the regular set of columns found in a relational table. This lack of fixed schema means that each entity can be self-describing. So often this is achieved by labeling each field with the name of the data that it represents. So for example, a non-relational collection for customer entities might look something like this. Now, a key aspect of non-relational database is that they enable you to store data in a very flexible manner, because non-relational databases don't impose a schema on the data. Instead, they focus on the data itself rather than how to structure it. So this approach means that you can store information in the more natural format that might mirror the same way that your applications might query and consume and use it. So if we take a look at this example here, the fields are prefixed with the name, and some fields might actually have multiple subfields. So for example, if we have a look at telephone, we can have a home telephone, a business telephone, a cell telephone. And these multiple subfields are denoted by enclosing them between square brackets. And so if we wanted to add a new customer to this non-relational data store, it's a matter of inserting an entity with its fields labeled in some meaningful way. Now, the application that queries this data must be prepared to actually pass the information in the entity that it retrieves. The data retrieval capabilities that a non-relational database can actually vary. So each entity should have a unique key value. For example, the ID needs to be unique. So the entities in the collection are usually stored in some key value order. For example, the key here is ID, name, telephone, and address. And the value would be 1, Mark Hansen, the phone numbers and addresses of Mark Hansen. The simplest type of non-relational database enables an application to either specify the unique key or a range of keys as the query criteria. And so in this example, the database would enable an application to query customers by ID only. Now, filtering data on other fields would actually require us to scan through the entire collection of entities, parse each entity in turn, and then apply the query criteria to each entity to find the matches. And so, for example, if we were to do a query that fetches the details of the customer by ID, we can quickly do so. But if we had a query that attempted to find all the customers with the UK address, for example, we would have to iterate through every entity, and for each entity, examine each field in turn. And so you can imagine a database that contains millions of entity records. This kind of query would actually take a considerable amount of time to run. And so you would typically query a non-relational database with its unique key value for each entity. Some of the more advanced non-relational systems supports indexing, much like the indexing in a relational database. So queries can then use the index to identify and fetch the data based on a non-key field. Some of these more advanced non-relational systems that supports this are, for example, Azure Cosmos DB, which is a non-relational database management system that's available in Azure. And so with this indexing, we can actually query non-key fields from a non-relational database. Now, semi-structured data is data that contains fields, and the fields don't have to be the same in every entity, so you only define the fields that you need on a per entity basis. The data must be formatted in such a way that an application can then parse and process it. And one of the more common ways of doing so to store the data for each entity and fetch it is using JSON. So JSON stands for JavaScript Object Notation. It's a format that's typically used by JavaScript applications to store data in memory, but it can also be used to read and write documents to and from files. So typically, a JSON document is enclosed in curly braces. Each field has a name followed by a colon and then the value of the field. The fields can contain simple values or could contain sub-documents, each also starting with its own curly braces. Fields that contain multiple values are held in arrays, and the arrays are the values that's denoted in square brackets. Inside these values, you can actually define whatever you like. So the important point to make here is that as long as you follow the JSON grammar, you can import any type of data into the value. Now, when an application reads a document, it needs to use a JSON parser because this JSON parser will then break up the document into its component fields and extract out the individual pieces of data. Now, Avro is a row-based format. So it was actually created by Apache. Each record contains a header that describes the structure of the data in the record. The header is actually stored as JSON, and the data is stored as binary information. So an application will typically use a header to parse the binary data and extract out the fields that it contains. Avro